Section 240.4 D of the National Electrical Code, or NEC, addresses the protection of conductors, and it is essential for ensuring electrical safety. Specific concern revolves around applying this section to motor loads. A scenario is presented where a test stand runs motor loads of just under 25 amps. When applying the 125% factor and consulting table 310.17 for the current rating at 75 degrees Celsius, a number 12 American wire gauge, or OG, conductor appears suitable. However, the challenge arises because the circuit protection will exceed 20 amps, which is the limit typically associated with number 12 AWG wire as per 240.4 D. The question is whether the application of 240.4 D is correct, especially considering the counterargument based on 240.4 G and the protection requirements outlined in Article 430 for motors. To clarify, the application of 240.4 D is indeed correct in this scenario. Section 240.4 D stipulates that the ampacity of a conductor must not be less than the sum of the currents of the loads supplied, plus 125%. In this case, the load current is just under 25 amps. Applying the 125% factor, we calculate 1.25 times 25 amps, which equals 31.25 amps. Therefore, the required ampacity is 31.25 amps. According to table 310.17, a number 12 AWG copper wire has an ampacity of 30 amps at 75 degrees Celsius. Since 30 amps is less than the required 31.25 amps, a number 12 AWG wire is not sufficient in this situation. Section 240.4 G comes into play when the ampacity of the overcurrent device protecting a circuit is greater than the ampacity of the conductor. In such cases, the conductor must be protected by an approved means other than the overcurrent device. Here, the circuit protection exceeds 20 amps, which is the ampacity listed in 240.4 D for number 12 AWG wire. Therefore, an alternative approved means of protecting the number 12 AWG wire must be employed, such as a motor overload relay. Article 430 provides specific protection requirements for motors. Section 430.42 states that motors must be protected against overloads by 1. A motor overload relay, or 2. Another approved device or system. In conclusion, a number 12 AWG wire is not adequate for a load of just under 25 amps when the overcurrent protection device exceeds 20 amps. The wire must be protected using an approved method, such as a motor overload relay as dictated by 240.4 G in Article 430. It is important to note that adhering to the current NEC requirements is crucial, regardless of past practices. The NEC is regularly updated to ensure the safety of electrical installations, and it is imperative to follow the most current code requirements. Now let's delve deeper into the specifics of conductor ampacity, overcurrent protection, and motor protection according to the NEC. Understanding these concepts thoroughly is crucial for safe and compliant electrical installations, particularly when dealing with motor loads. The ampacity of a conductor is the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors influence ampacity, including the conductor material, size, insulation type, installation method, and ambient temperature. The NEC provides tables such as 310.15 and 310.17 that list the ampacities of various conductors under different conditions. These tables are essential for selecting the appropriate conductor size for a given application. Overcurrent protection is a critical safety measure designed to protect electrical circuits and equipment from excessive current, which can lead to overheating, insulation damage, and fire hazards. Overcurrent devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. The NEC specifies the requirements for overcurrent protection in Article 240. These requirements include the selection and coordination of overcurrent devices to ensure that they provide adequate protection without causing nuisance tripping. Motor protection is a specialized area of electrical protection that addresses the unique characteristics of motors. Motors can draw high inrush currents during startup, and they are susceptible to overloads and faults that can cause damage or failure. Article 430 of the NEC provides detailed requirements for motor protection, including overload protection, short-circuit protection, and ground fault protection. Overload protection is designed to protect the motor from sustained overcurrents that can cause overheating and insulation damage. This is typically achieved using motor overload relays, which are devices that monitor the motor current and trip the circuit if the current exceeds a set level for a specific duration. Short-circuit protection is intended to protect the motor and the electrical system from high fault currents that can occur during a short circuit. This is typically provided by fuses or circuit breakers that are sized to interrupt the fault current quickly. Ground fault protection is designed to protect personnel from electric shock hazards that can occur if a motor winding comes into contact with ground. This is typically accomplished using ground fault circuit interrupters, or GFCIs, which detect small imbalances in the current flowing through the circuit and trip the circuit if a ground fault is detected. Now let's revisit the specific scenario presented earlier. The question involves a test stand running motor loads of just under 25 amps. The initial assessment, based on the 125% factor and table 310.17, suggests that a number 12 AWG conductor might be suitable. However, a concern arises because the circuit protection will exceed 20 amps, which is the limit typically associated with number 12 AWG wire as per 240.4. To address this concern, it's important to consider the following points. Firstly, the 125% factor is applied to the motor's full load current, which is the current the motor draws when operating at its rated horsepower and voltage. This factor is intended to account for the motor's starting current, which can be several times higher than the full load current. Secondly, Table 310.17 provides the ampacities of conductors under specific conditions of use, including the insulation type, installation method, and ambient temperature. It's important to select the appropriate ampacity table based on the actual conditions of use. Thirdly, 240.4. Specifies the overcurrent protection requirements for conductors. This section states that the overcurrent protection device must not exceed the ampacity of the conductor it protects, unless otherwise permitted by the NEC. In the case of motor circuits, the NEC allows for higher overcurrent protection ratings to accommodate the motor's starting current. However, the overcurrent protection must still be sized to protect the conductor from overloads and short circuits. Fourthly, 240.4. Provides an exception to the general rule that the overcurrent protection device must not exceed the ampacity of the conductor. This section allows for the use of a larger overcurrent protection device if the conductor is protected by an approved means, such as a motor overload relay. Fifthly, Article 430 provides detailed requirements for motor protection, including overload protection, short-circuit protection, and ground fault protection. These requirements are intended to ensure that motors are adequately protected from damage and hazards. In this specific scenario presented, a number 12 AWG conductor with an ampacity of 30 amps at 75 degrees Celsius is not sufficient for a load of just under 25 amps when the overcurrent protection device exceeds 20 amps. This is because the required ampacity, calculated using the 125% factor, is 31.25 amps, which is higher than the ampacity of the number 12 AWG conductor. To comply with the NEC, an alternative approved means of protecting the number 12 AWG wire must be employed, such as a motor overload relay. The motor overload relay should be sized to protect the motor from overloads, while the overcurrent protection device should be sized to protect the conductor from short circuits and ground faults. It's also important to ensure that the motor is properly grounded to minimize the risk of electric shock hazards. The grounding conductor should be sized according to the requirements of Article 250 of the NEC. Furthermore, it's important to note that the NEC is constantly updated to reflect changes in technology and industry practices. Therefore, it's essential to stay current with the latest edition of the NEC to ensure that electrical installations are safe and compliant. In addition to the specific requirements discussed above, there are several other factors to consider when designing and installing motor circuits. These include the motor's voltage, horsepower, and duty cycle, as well as the ambient temperature and the presence of any hazardous materials. It's also important to follow the manufacturer's instructions for the installation and operation of the motor and its associated components. By carefully considering all of these factors and following the requirements of the NEC, it is possible to design and install motor circuits that are safe, reliable, and compliant. Understanding the nuances of the NEC, particularly sections like 240.4, D240.4, G, and Article 430, is crucial for electrical professionals. These sections provide the foundation for ensuring that motor installations are not only functional but also safe and compliant with the latest electrical standards. The proper application of these codes protects equipment, prevents hazards, and ensures the longevity and reliability of electrical systems.